we look into applications of Laplace transform in this video. Before we really get into applications, for example, to solve the ordinary differential equations to start with. So, what we do is we have two more results, that is about the link between the initial value. If you have f of x is your function, bar of s is your Laplace transform, initial value of the function f, that is f of 0, and if you, what is its relation f of 0, what is its relation with the Laplace transform f bar of s. So, this is about the initial value theorem, and also about if you have fx, a function, and its Laplace transform f bar of s, and if you look at s goes to infinity f bar of s, with that limiting value of or f at infinity, if you want to look at function f at infinity, if it exists, what is its relation with Laplace transform f bar of s. So, these two things can be used in applications in solving the differential equations. So, we will use that, but before I will do these problems, let us just quickly get these two results, that initial value theorem and final value theorem. So, let me write this initial value theorem. So, this tells you that if f bar of s is Laplace transform of f of t, which is function of s. So, if it exists, then this limit s goes to infinity f bar of s is equal to 0. So, using this we can also get, also I will just write this limit s goes to infinity s times f bar of s, this one is nothing but a limit of f of t as t goes to 0, that is actually f of 0. Okay. So, if f is a continuous function at 0, so this is 0, so this is what it happens. Okay. In particular, you can have this result. So, this is what exactly is useful for us. So, we need this. Let us prove simply how we do this. So, to start with, we just look at this part. So, that is straightforward to see. So, let me choose this s goes to infinity f bar of s. So, what is this value? This is actually equal to, so limit s goes to infinity integral. So, this is by definition 0 to infinity f of t times e power minus st dt. Because this integral is uniformly convergent integral as a function of s, so I can take this limit inside this integral. So, that will make it 0 to infinity limit s goes to infinity e power minus st, and then anyway this is a function of t, that is nothing to do with s. So, this is dt. So, this becomes, as s goes to infinity, is actually 0, okay, because this limit is 0. So, you have this is 0. So, this is straightforward. Suppose f is differentiable function, okay. So, let me use this if f is differentiable function, if f bar of t exists, then this is also true. So, this is what we will show, okay. So, the second part is this, if f bar exists, you look at the same way, this s goes to infinity Laplace transform of f dash of t, okay. If f bar of t exists, and if this Laplace transform of f bar of t, if this Laplace transform exists, this also should go to 0, okay. So, this also should go to 0 by the earlier argument. This is again limit s goes to infinity. So, by the same argument you can show that f of t power minus st dt, this is limit s goes to infinity e power minus st times f dash of t dt. This is actually 0, okay. But then what does it mean? So, this means we already have seen that this limit s goes to infinity, Laplace transform of the derivative of the function is s f bar of s minus f of 0, this has to be 0. So, in the place of this I wrote this is the definition, this is how we calculated Laplace transform the derivative of the function. So, this is nothing but limit s times f bar of s as s goes to infinity is nothing but this is a constant that is in terms of f of 0, which is nothing but for a function, a continuous function at 0, this is the limiting value is same as that. So, this is exactly what we need to show here. Okay. So, this is the initial value problem, which is just by using a straightforward use of definition of Laplace transform, and then use uniform convergence of the integral Laplace transform, that integral definition of the integral definition of the Laplace transform, which is uniformly convergent, so that you can take the limit inside the integration. So, that gives the result straightforward. So, this is one result, and the other one is a final value theorem. Final value theorem. So, this may be also be used in the applications as and when it comes, we will see. So, final value theorem says if f bar or of s is. So, let us take a simple particular form of f bar of s. Let us take this as this way, p bar of s and q bar of s, where p and q bar of s are polynomials. Okay. So, where p bar of s and q bar of s are polynomials in S, and obviously degree of Ps is smaller than degree of degree of P bar of S is smaller than degree of Q bar of S. So, assume we have such a Laplace transform, and assume also that Q bar of S roots also roots of all roots of this have a negative real part. That means you have poles only on the negative side of S plane. So, except possibly at S equal to 0, okay, except possibly one root at S equal to 0. This can be 0 at S equal to 0, okay. One root can be at S equal to 0 if you allow. So, that S is positive. So, you have that C, the C minus I infinity to C plus I infinity, that in inverse transform S is defined are for all S positive. So, that you can finally what you want is this limit f bar of S as S goes to 0, because this has this f bar of S has all the poles which are the roots of q bar of S, which are in the negative side. So, S is well defined on the positive side. So, I can take the limit S goes to 0. So, f bar of S, this is nothing but, so what you get is integral 0 to infinity f of t dt. Okay. If you have something like this, so which is in a simple form, or any f bar of S, which is the limit which is the Laplace transform of some function f of t, and if you have it is well defined for S positive, okay. If f bar of S is well defined for S positive, that is possible only if this function, this Laplace transform should have all the negative, all the roots, all the poles, all the singular points on the negative side of this plane, S plane, S complex plane. So, that S positive, it is analytic function which is well defined, so that you can think about its limits as S goes to 0. So, that is the only assumption. So, that is these assumptions are simply to make sure that this limit is well defined. Okay. So, finally, you see that this is the value you will get, and this is one also like earlier, if it is a differentiable function, if f bar of t exists for a, or rather for a differentiable function, okay, and you can have this result that S goes to 0, S times f bar of S, this is equal to limit f of t as t goes to infinity. This is why exactly it is called final value theorem, because f at t as t goes to infinity, there is a final value, that is f infinity, if it exists. Okay. So, this is exactly the meaning. So, proof here also it is simple, you simply write what you want. So, this is what you want for a suitable f bar of s for which s is positive, it is well defined. So, that I can talk about this limit s goes to 0, f bar of s, this limit s goes to 0, f bar of s by definition e power minus st f of t dt. Okay. So, again this is a Laplace transform. So, this integral is uniformly convergent. So, that I can take this limit inside as a s variable. So, you can take this inside, limit s goes to 0 e power minus st f of t dt. So, this is this limit, if you calculate, that is 1, s goes to 0. So, you have 0 to infinity f of t dt. Now, this is also second result is also simple. If f bar t exists, what happens here? F bar of t, a Laplace transform of this as s goes to 0 is equal to integral 0 to infinity. So, if I apply the same result for f bar of t, you see that f bar of t dt. So, this is nothing but f at infinity minus f at 0. But we already know that this this is limit s goes to 0, definition of Laplace transform for a differentiable function f bar of f dash of t is s f bar of s minus f of 0. So, that is the when we have seen this as a property of the Laplace transform. So, this is your left hand side is equal to right hand side is f infinity minus f of 0. So, this is a constant. So, limit s goes to 0. So, this gets cancelled both sides. So, you end up getting what you want. So, this limit s goes to 0, s f bar of s equal to f at infinity, which is nothing but limit f of t as t goes to 0. If it exists as a finite number, this has to be a limit of f of t. So, that is exactly what you need to show. So, this is called the final value theorem. So, these are the two results which you will keep in mind while solving the ordinary differential equations, which you will see soon. So, when you have some arbitrary constants involved in the Laplace transform of the unknown function, and you may have to use one of these, but what is given is the unknown function, the solution of the differential equation initial value, if it is given, that means x of 0 is given, and you have to relate with its the Laplace transform of x of t, that is x bar of s, for which if you look at the s goes to infinity, you know exactly what it means, okay, because of the initial value theorem. Similarly, you can use the final value theorem to make use of this in the applications. So, keep these two results, these simple results in mind. Let us do this applications of Laplace transform. Applications of Laplace transform. So, start with solutions of ordinary differential equations. Okay, we solve solutions of ordinary differential equations. So, how do we solve this? Let us start with ordinary differential equation, means you have one dependent variable and one independent variable. So, you have a relation between unknown dependent variable and its derivative. If it is order, for first order differential equation, you will have unknown dependent variable and its one derivative. So, you will have a relation between this along with independent variable. So, you will have a relation between dependent variable and its derivative and independent variable. This is called ordinary differential equation. So, we look into it some linear first order ordinary differential equation. Let me take specifically, let us solve some example. So, how do we solve this first order? First order case, first order ODE. Let me take this first order ODE. How do we solve? So, example, let me start with dx by dt. X is the dependent variable, t is the independent variable. then this is the first order, this will have a derivative of the dependent variable, p is a constant, x is again independent variable, this is equal to right hand side any function of t. So, given function of it, that is forcing. Okay. So, this is the first order a linear ODE. So, this how do we solve this? So, you can use this because t is positive side. If your differential equation, if your domain is 0 to infinity, you can use your Laplace transform. Of course, you have initial values x at 0, the boundary, this is your domain. So, t is positive. So, t is running from 0 to infinity. So, this is the boundary also initial value. So, this is called initial value time. So, this x of 0 is the first order. So, you have to provide one initial value at x at t equal to 0, that is x is 0, which you call it a constant. Okay. So, where a and p are constants. Let us take this. So, how do we solve? So, let us solution, let me apply a Laplace transform to the equation. So, apply Laplace transform. To the equation, we get what we get is, if you apply Laplace transform to this derivative, so you get s times x bar x of t. If you apply, this is x means x of t, it is a dependent variable. So, you have x bar of s, that is a Laplace transform, minus x at 0. So, this together is the Laplace transform of the derivative of x, plus p is a constant and you have x bar of s, and this is equal to f bar of s. Assume that f of t for which you have Laplace transform exists. So, this gives me, and now you have x of 0 you can use here initial value, that is a. So, you have x bar of s is equal to f bar of s plus a divided by s plus p. Okay. So, now we can take the inverse transform, taking inverse transform to get the solution. Get the solution x of t. Left hand side, if you take the inverse Laplace transform, you get x of t. On the right hand side, so you see a is a constant, a divided by a is a constant comes out, Laplace inversion of 1 by s plus p plus Laplace inversion of f bar of s times 1 by s plus p. So, what is this one? This is actually equal to a times, this is e power minus pt. Okay. So, Laplace transform of this is 1 by s plus p. So, I have written this, plus here this is the Laplace transform of f of t, this is the Laplace transform of e power minus pt, and this is f of t. So, you take the convolution of this, and that should be for which Laplace transform if you take, that is what exactly you will get f bar of s and this. So, Laplace transform of this is nothing but this whole f bar of s times this. So, when you take the inverse transform, Laplace goes, so you end up simply getting this one. So, let me write this definition of this convolution. So, you have 0 to t. So, you can write e power minus p or f of tau, e power minus p. In the place of t, you have written, you write t minus tau d tau. So, that is exactly your definition of the convolution. So, this is exactly you will get as if you apply other methods to find the solution of this linear equation. So, you have this e power minus pt comes out because it is nothing to do with the tau variable. So, you end up getting 0 to t f of tau e power p tau d tau. So, this is the solution of your differential equation that you started with as a first order linear ODE and with the initial value. So, this is how you can solve it by applying Laplace transform, provided the boundary the domain of the differential equation is 0 to infinity. So, let us move on to solve the second order equations second order linear ODE you can solve similarly, second order linear ODE. So, of this form, so let us choose some form. So, for example, d square x by dx dt square, x is the dependent variable, t is independent variable, plus 2 times let me use this just for convenience, I am considering this, p is a constant, dx by dt plus qx, q times q is also constant, x is a dependent variable, and you have f of t, if t is positive, and this is a second order equation. You should provide 2 initial conditions, that is at x equal to 0, let us call this a, and x dx by dt at t equal to 0, at x dx by dt, that is also called x dash of 0, which is nothing but some b, let us choose given the constants. Okay. So, where p, q, a, b are constants. If you have in this form, you can solve it, because you can take the Laplace transform here, Laplace transform. If it is a q is a function of t, which possibly you may have to, it may be difficult to find the Laplace transform and get finally. So, that may be difficult. Not all equations you can solve. Some simple, some specific forms, for example, like this you can solve. So, if you apply, so solution is by applying Laplace transform, apply a Laplace transform to the equation, get what we get is a derivative, second derivative of this, we know that this is the derivative is s square x bar of s minus s times x at 0 minus x dash at 0. So, this is the derivative, this is the Laplace transform of the second derivative, plus 2 constant p times s x bar of s minus x at 0. This is your definition of Laplace transform of the first derivative, and then plus q is a constant, and you have Laplace transform of x, which is equal to f bar of s, which you have taken Laplace transform of f of t. Now, you can use the initial values x of 0. So, you have s square, collect the terms of coefficients of x bar. So, you get 2 p s plus q times x bar of s is equal to f bar of s plus plus you can have this s times coefficient of x of 0, that is a here, a here. So, you have x of 0 is a, you have s plus 2p when you bring it to the right hand side, and the other one is x bar of 0, that is b. So, you have b plus b, that is it, right. So, you have this. So, you have this implies x bar of s is f bar of s plus a times s plus 2p plus b divided by s square plus 2ps plus q. So, for which if you take the Laplace transform, Laplace inversion, so you can get your solution. So, take the inverse transform, inversion gives x of t. So, that is simply Laplace inversion of f bar of s times 1 by s square plus 2ps plus q, plus here this becomes a times Laplace inversion of, a is a constant. So, a inversion of Laplace inversion of s plus 2p divided by s square plus 2ps plus q. Of course, this is also constant, so you can put it here. So, this is the second order in S polynomial, this is the first order in S. So, you can get this solution as this way. So, one way to find these inversions are just to write this in a nice form, that is a Laplace inversion of, put it together. So, let me write in the denominator this second order polynomial, I write like s plus p whole square plus if you write this 2ps comes out p square. So, you have a minus q minus p square. So, that is exactly how to use as something which I call, if I call this as n square, okay, q minus p square that is exactly, let me call this some n square. So, you call this n square, this is on surface. So, because we know that certain form s plus p square by plus a square 1 by s plus c whole square plus a square. So, if it is like this s plus c, we know it is Laplace inversion. So, put it in that form, let me use that form. So, that you have s plus p here. So, s plus p already 1 here times s plus 2p. So, you have a here. So, a comes out, a times s plus p plus b plus p, that is anyway constant, b plus. So, b is actually b by a if you take here. So, you have b plus pa, which is a constant, plus f bar of s. So, let me put it in this form, so that you can write directly what is its inversion. So, inversion is a comes out here, a comes out, Laplace inversion of s plus p divided by s plus p whole square plus n square plus b plus pa times L inversion of 1 by s plus p whole square plus n square. So, you need this n here to get the form. So, you have divide by n. So, I divided and multiplied. So, that n goes, which is second term you get. And the other one is Laplace inversion of f bar of s in times n divided by s plus p whole square plus n square. So, because I multiply 1 extra, so it comes out. So, I have 1 by n here. So, if I write like this, now you can take the inversion here depending on what is your n. N is n square is this. So, n square is either it is positive or negative, it can be 0. So, in each cases you can easily see what it is. Okay. If it is a positive case, so let me use if n square, which is equal to q minus p square, if this is positive. Okay. So, you have a positive plus, that means a plus sign n square. So, this is what we have seen. So, in this case your x of t, there is your x of t here, x of t is a times Laplace inversion of this is e power, because of s plus p, e power minus pt times Laplace transform of s by s square plus n square, that is cos n t. Okay. So, this together is this one, Laplace transform of this is this one. So, plus b plus pa by n times, here this is e power minus pt sin nt. Okay. And then here 1 by n times, and this will be your convolution of f of t, that is 0 to t f of tau, and here e power minus p t, in the place of t you put t minus tau, and this will be sin n times t minus tau d tau. So, this together e power minus pt sin t, that is the Fourier transform of this, Laplace transform of this is this one. So, convolution, have to wherever t is there, you have to replace t minus tau. So, in this place I have written t minus tau. So, you get this one. So, here you can easily see that t is, it is nothing to do with t. So, you can write this outside e power minus t pt. So, that you have together here you have only p tau. This is exactly a solution if n square is positive. If n square is 0, this is the case, x of t, this is straightforward. So, you have 0 here. So, a times L inverse of 1 by s plus p, that is e power minus pt. So, 1 by s is Laplace transform of 1. So, because of s plus p you have e power minus pt plus b plus pa by n times, here when n equal to 0 this goes to 0. So, n anyway you can remove this n and goes. So, you do not have. So, you have b plus pa L inverse of 1 by s plus p whole square when n equal to 0. So, that is t times that is 1 by s square is Laplace transform of t. So, you multiply with e power minus pt. So, that is the Laplace transform of this is 1 by s plus p whole square plus Laplace inversion of f bar of s and 1 by s plus p whole square, that is simply convolution of f of f and t into e power minus pt. So, t minus tau times e power minus p t minus tau d tau. So, t you can bring it out here. So, you have e power minus pt, so that you can write p tau here d tau. So, this is the solution for in this case. Similarly, if n square is which is q minus p square, if it is negative, and you can write this as s plus p whole square minus n square, that is n square is positive with minus sign. So, in this case you can have x of t as simply cosines will become cos hyperbolics. Okay. So, you have a times e power minus pt cos hyperbolic n t, because you have in this case it will be minus n square with n square being positive, because this is negative. So, that is nothing but q minus p square is minus n square with n square is positive with but negative sign. So, that is you have s plus p whole square minus n square in the denominator. So, if you write like that, so you end up getting so you can write minus here. So, minus n square, but I multiply only n without only here you get a minus n. This I am multiplying, just this I am adding actually. So, once you have minus n square, I am only multiplying and dividing with the n. So, here you get a negative sign, so that you have b plus pa by n times you get here this is e power minus pt sin hyperbolic nt, and then plus again so same way minus 1 by n, this is convolution of f of tau, this is going to be sin hyperbolic n t minus tau times e power minus pt. So, e power p tau d tau, so that I can write e power minus p tau here minus pt outside just like earlier. Okay. So, this is the solution finally. This is in this form if you have n square is a negative sign. So, whatever may be the case so as such directly if you can find by some other means, if you can find this Laplace inversions, you can easily write in a different form your solution. And this by this technique you by known functions you bring in and try to recognize its Laplace inversion and write in the nice form. Your solution you represent in these elementary functions like sine or sine hyperbolic depending on the value of this n. So, the same technique you can apply for higher order equations. So, you can also apply the same technique for higher order equation. I just may write let me take higher order equation, higher order linear ODE. So, let us take nth order ODE. If you have this solve this linear equation with n constant coefficients, let me take. So, if I take d power n x by d t power n, this is the nth derivative plus some constant a1 times d n minus 1 x of d t power n minus 1 and so on, you end up getting a n, so that no derivative. So, x simply a n times x equal to, let me call this some phi of t. So, t is positive. If t is positive, you can apply your Laplace transform. And of course, you because it is the nth order differential equation, you should provide some initial conditions x of 0, x dash of 0 and up so on up to x nth derivative n minus 1th derivative at 0. You have to provide, let me call them, let's call this some x naught, x1 up to x n minus 1. Okay. If I call this is your initial values. Okay. This is your differential equation. So, this initial value problem you can solve again by Laplace transform. So, we will see why is it possible. As a general case, if you apply this for the nth derivative. So, let me write this apply Laplace transform. Laplace transform gives s power n x bar of s minus s power n minus 1 x at 0, that is x at 0 as x naught. I use directly x naught minus s power n minus 2. Now you have x dash of 0, that is x 1, and so on. Finally, you end up getting minus s times x n minus 2, that is x n minus second derivative. Okay. That is x n minus 2 minus x n minus 1. So, this is the derivative, this is the Laplace transform of nth derivative of a function x of t. And then you multiply. So, for second term again you write in a similar fashion. If you write this as s power n minus 1, because n minus 1th derivative x bar of s minus s power n minus 2 x 1 and so on, n minus 2 x naught, here x start with x naught and so on. Finally, you end up getting x n minus 2 and so on. You getting a 2 times again s n minus 2 times x bar of s minus s power n minus 3 x naught minus and so on, finally getting x n minus 3 and so on. You get finally a n minus 1, a n minus 1, one derivative, that is s x bar of s minus x naught plus a n, the last last term, that is a n x bar of s. Right hand side is phi bar of s, because phi of t. So, if you have like this, you collect the coefficients of all x bar of s. What you end up is, let me write, you can see directly this coefficient of this is s power n. So, you have clearly a polynomial in for degree n, s power n here, plus a 1 s power n minus 1 plus a 2 s power n minus 2 here. Finally, you end up getting s into a n minus 1 plus a n. So, this is your nth degree polynomial as a coefficient of x bar of s. Right hand side, take everything to the right hand side, you see that a phi bar of s plus here I collect the coefficients of x naught coefficient. If you collect, that is a polynomial in s with degree n minus 1, and here plus a1 if you collect the coefficient of x naught. So, you have s n minus 2 and so on. Okay. So, finally, you are getting coefficient of x naught, that is minus, so it's plus, when it bring it this side, there is plus. So, you have a n minus 1. Okay. And up to, so you do the same way, and finally, you get the coefficient of x n minus 2. X n minus 2 is a coefficient of x n minus 2 is, this is x naught. Similarly, x 1 x 2 coefficient you can write. Finally, x n minus 2 coefficient is s here, and then s, and where else you get as your x n minus 2, that is going to be only this term will have next term. So, that is s plus a 1, and finally x n minus 1. So, here, so this is the only thing that is remain. So, plus x n minus 1. This is exactly you have coefficient. So, this is your polynomial. So, let me call this p n of this, if you call this as a p n. So, x bar of s is now phi bar of s plus x naught times p n minus 1. Let me call this so polynomial of polynomial in s with degree n minus 1 up to this, here it is polynomial of degree 1, this is simply a constant. This whole thing divided by or together. So, together this is the polynomial of degree s minus 1. So, this is polynomial of degree let me call this p n minus 1 degree of s. This p n minus 1 is, this whole thing is my p n minus 1 of s, because this is a polynomial of degree n minus 1. You have this one is a polynomial of degree q of let me call this q n of s, because the degree is n. So, you have q n of s. Of course, you have, because it is bar, let me call this bar, puts bars. Okay. So, let me call them as bars. So that you have taking the inverse Laplace transform gives Laplace transform gives x of t as your solution, because you have already used all the initial conditions. You have as a Laplace inversion of phi bar of s times 1 by q n of s bar. So, this is, you should know this, you can get it by 1 by q bar of s, you can write it as a partial fractions, or by general method of finding Laplace inversion you can find, and other thing also you can do the same way. So, either Heaviside expansion or partial fractions method, or a general Laplace inversion by the contour integration technique you can calculate, and you can write your Laplace inversion here. That will be the solution of the higher order equation for t positive. Okay. So, this is the general procedure. If you can follow, if you have a constant coefficients equation, you can easily solve this type of equations. They come in the applications, for example, harmonic oscillator, some equations, ordinary differential equations you will come across in the harmonic oscillators, also in the electric circuits. So, these ordinary differential equations you will come across. Okay. So, as and when they come, you can you just use this technique to solve them. We will try to see the system of equations and also other type of special type of ordinary differential equations we will solve in the next video. So, before we wind up today, let me do some higher order equation, higher order linear equation. Let me solve to show as an example here for this general technique. Solve this d cube x by dt cube, third order equation. Let me choose dx square by dt square, of course with constant coefficients here, only 6 times dx by dt is equal to 0. So, if this is what is their equation for t positive, this is important. Okay. Only if t belongs to full infinity, you cannot do this, because this is the domain is only t positive, you have to apply your Laplace transform. Otherwise, you may have to split this equation into 2 parts, one is t positive, one is t negative side. Each part you have to do separately and get it and then combine it together. So, that is more cumbersome. So, there is you can instead you can use other techniques to find the solution of that equation. So, let me use, so for this is the case, initial values are x at 0 is 1 given, x dash at 0 is equal to 0, and x double dash of 0, because the third order, so after second order you have to provide the solution initial conditions. So, these are the initial conditions. Okay. So, solution can easily work out, like earlier if you write, you see applying Laplace transform gives, what you get is x bar of s. So, let me write this directly. So, right hand side is 0. So, phi of t is 0. So, we do not have that term. So, you have simply that Pn minus 1. So, that is this is the third order. So, you have a second order term that will come and as a numerator s square plus s minus 1. The denominator cube root is third degree polynomial in s, that is s cube plus s square minus 6s. So, s is common. So, you can write s you remove, put it outside, do it write like this. So, this is your x bar of s. So, inverse Laplace transform will give you inversion gives x of t, that is a Laplace inversion of s square plus s minus 1 of s times s square plus s minus 6. So, this is exactly your Laplace transform, your solution of this third order differential initial value problem. So, how do we find this inversion? So, this is, you can use the partial fractions method. You just get the partial fractions, L inversion of, I write this partial fractions, if I may write 1 by 6 times, you get a by 1 by a by s plus b by s plus 3. You have this is s plus 3 and s minus 2. Okay. So, if you do like this product of these two, so you have 1 by s plus 3 b by this, the b will give me 1 by 3. and c by 1 by s minus 2, c is 1 by 2. So, you do the partial fractions, this is what you will get. So, that you can easily see that 1 by 6 times 1 by s Laplace transform is simply 1, inversion is 1, plus 1 by 3 times e power minus 3t plus 1 by 2 times e power 2t. So, this is your x of t. So, this is exactly your solution by Laplace transform method for this initial value problem with these 3 initial conditions for this equation. If you try to solve, this is how you get the solution. Okay. So, we will also solve, we can also solve linear coupled system of equations, system of ordinary differential equations you can solve, that we will see in the next video, along with some special equations you can solve by Laplace transform technique. Okay. Thank you very much.